Welcome to the APL quest. Today's quest has us imagine two circles that are touching each other, and one of them stays where it is. The other one rolls on the first one's surface or circumference all the way around until it reaches the place where it started. Now, obviously, it depending on the exact sizes of these two circles, then it may not end up in the same. It might, while it's in the same position relative to the stationary circle, it may not have the same orientation, may not be pointing in the same direction again. And so today's problem, which is the seventh from the 2014 round of the APL problems on the competition, is to see how many times does the circle that's rolling need to go around until how many times does it need to turn around itself so that until it has rolled all the way around the stationary circle, but also is pointing in the same direction, and I mean the same orientation as the way it started. There are different ways that we can attack this. Let's just start by actually simulating the problem. And we can use, and since we have two arguments here, we have the size as left argument of the stationary circle, and then we have the size of the mobile circle, the one that's rolling around. And officially they're given as diameters, but it doesn't really matter because the circumference, of course, is just a constant times the diameter, and that's the same for both. So that kind of goes out of the equation. But what we want to see is whether the amount of revolutions that we have done on the mobile circle times its size ends up with something that that we can divide the stationary circle by. Sorry, something that that can be divided by the stationary circle. Okay, so the way we can write this up is we are done if there's no division remainder when we are dividing by the stationary circle. And how far we've gone so far, well, we're going to use an operand for that. So that's how many revolutions we've done of the diameter, well, actually the circumference of the mobile circle. And if that divides, then we're done. And so that's the number of revolutions. Otherwise, we are going to try again, but this time we're going to increment the counter of revolutions. So we take one more revolution of the mobile circle, and then we feed that in to the same operator. So this is an operator, not a function. So the arguments stay constant, and the operand increments every time. And then we just need to start with a1. So this is a recursive solution. It keeps incrementing and calling itself. So we can say a stationary circle of diameter, or for that sake, circumference 10, and then we have a mobile one that's 5. So the 5, after it has rolled one time around itself, then it's on the opposite side, and then it rolls one time again around itself, and it comes back to where it was. If we try to flip the 2, then we only need one revolution of the mobile one. What's happening is that it only needs to go half a turn to come back to where it was, but it will keep going for another half a turn in order to come back and face the same direction that it started with as well. And we can try all the possibilities by making a table of this. So this is an outer product, and then all the numbers up to 10, and then that gives us a full table of the revolutions. There's one interesting issue, and that is 0. Now, it doesn't really make sense that a mobile circle should have a diameter and therefore circumference 0. It's point-shaped because it doesn't matter then how many times it will turn around itself. It's never going to get anywhere. So every time around, it will move 0. It will not move at all, unless also the left argument, the stationary circle, is point-shaped, in which case nothing can really move. And it doesn't really make sense to ask how many times. I mean, any number of times would be good. 0, 1, 2, infinite. So you could say the result is 0, or you could say that 1, or after 0 times it's also turned 1 full revolution around. The 0, 0 case doesn't really matter. However, if the stationary circle is 0, then the result is most certainly 0 because we don't need to get anywhere. Even though the mobile circle has the ability to revolve, it doesn't actually need to revolve. So we can handle this additional case by adding in an extra guard. So if the left argument, that's this circle standing still, is 0, then the result is 0. Otherwise, we just continue as before. And now we can go and make a test case where there's even a 0 on the left, but not on the right, as that doesn't really make sense. And we can see you get a row of all zeros there, of course. Right, so this is one way to do it. This was recursive. Let's try to do an iterative way. Here we just start off with a count of 0, and then we increment as we go along, and until it works out. It's a little bit. It's much shorter, but it's a little bit more involved. So the way we can do it is we start off with 0, and then we need to increment it. And we want to increment it until our condition has been fulfilled. Now, what is that condition? That is that the left argument, because we're comparing the previous and the next iteration, and so that would be the left and right argument of our comparison function, which is the one that determines when it's true, then we have fulfilled our condition. So when that multiplied by the circumference of the mobile circle evenly divides the circumference of this circle that's standing still, then we're done. And so we should get exactly the same here as well. But again, we have a problem with 0, because if we start off with 0 on the left, then we're going to, we can try it. If we have 0 on the left and say 2 on the right, then the first time around we'll try to apply this function. So we add 1, so we get 1 and 0, and then we want to check if it divides division remainder. So let's try that. So we can just do it like this. Right here. So if we start with 0 here and say we have 2 and then we get 0, and then we want to stop. However, once we increment it, then we get the full remainder, because 0 doesn't add up to anything. In effect, what happens is that if we try to run this with a 0, then we'll go into an infinite iteration. We'll never get there. So let's interrupt that. And then we can redefine I to have the same kind of stop guard as we did with the recursive version. So if there's a 0 on the left, then we stop with a 0 right away. Otherwise, we can start iterating. Okay, how do they compare in performance to each other, the iterative version and the recursive version? Let's copy in CMPX. from defense. And then we can compare them. We can make the table a little bit bigger and try them. So let's say the stationary one is 0 and all the numbers up to 100. And then the mobile one are all the numbers up to 100. And then we can compare all the possibilities with the recursive version and all the possibilities with iterative version. And the iterative version is much faster. And that's probably because we're not entering into any new functions, calling again and again, not binding together an operand with the operator over and over again. We're just staying in the same place, just running the power operator. But we can do much better than this by using some number theory, because think about the way that we're describing this. If this multiple divides, so really what we want to find out is what is the smallest number that we can multiply with to be divisible. And so we can express this in terms of the greatest common denominator or least common multiple. It actually comes out very much the same. So we want to divide. So let's say again we have 10 on the left, and then on the right we have 5. And so the least common, the greatest common denominator between the two is 5. So that means we can divide both of them by 5. And then we can see, well, if that's the case, then how many times 5 do we need to get in order to get all the way around the stationary one? So we just divide the left argument by that. So that's one way to state it, using the greatest common denominator, or its greatest common divisor. Oppositely, we can also look at the least common multiple. So here we are asking what's the smallest number that we can multiply up with these two numbers in order to match each other. So that's 10. That would be 1 times 10 gives 10, and 2 times 5 gives 10 as well. And then we can divide that by the right argument. So this is saying that in order for these to match up, then we need to have traversed 10 or to go all the way around. And since the right argument is this actual size of the moving circle, then the total distance divided by its circumference will give us how many times we need to go around. And so we can define this using the least common multiple as well. Now, there's an interesting thing about these two functions, g and l here, and that is they are really, really amenable to write in a tacit version. Why is that? Because let's look at g. If we think of things in terms of functions, then here we have a function application between the arguments, and then we have a function that takes that result as its argument. Now the only problem is here on the left, there's no function being applied between the left and right arguments, giving us a full fork. However, we could say there is one, namely the density function of the left argument. So if we wrote it like this instead, then effectively this function would select the left argument, which means all this we can remove all mention of our arguments, making everything point free or tacit, like this. Oops. And then a parenthesized function is just the function itself, and then we have parentheses around our fork. That gives us this fork as well. And we can do exactly the same thing for the function L. Here again, there's an implicit identity function that selects the right argument. So we can remove all the mentions of arguments, and then we're done. And now if we compare these, so we know that I was the fastest one of the two from before, the iterative version. So let's compare the fastest of those, of R and I, with these two number theoretical functions, G and L. And we should see that these, so to say, built-in functions, where pretty much everything we need to do is built into the language, are going to be much faster. If we try to just race them against each other, then we'll find that it doesn't really make a difference which ones that we use. They are all built on the same exact principle. Thank you for watching.